steps that you have to remember. Okay, so I'm going to copy this whole thing if I could. Okay. So now we are going to do failure analysis. So we are going to look at elements. Okay, we are going to look at element A, element B, element C, element D. We are trying to quantitatively identify which element has the highest stress. Okay, so by looking at this, we can tell. Okay, so if we look at the term stress X is equal to minus Px over A, right? Element A, B, and C, due to the axial loading, all of them will C minus Px over A. All of them. Okay, all of them will see the minus Px over A. So from Px over A, we can't what? We cannot tell which one is the more critical element. Okay, and now the next one that we're going to look at is we're going to look at stress X is equal to mz over izz multiplied by y. So element A will have positive mz over mz multiplied by y over izz, right? Point B is at the centroid, right? So it's equal to what? 0. Okay. And then point C again is at minus mz multiplied by y over izz. And then point D is equal to 0. So based on normal stress, right? Based on the normal stress, we know that element C is the one that we have to calculate based on normal stress. Okay. Now, if we were to look at shearing stress, so the shearing stress is due to the torque is equal to TR over J, and all of them will see TR over J. So from here we have identified that element C, right? Element C right, is the most critically stressed. So where failure will occur, it will start from where? It will start from element C. Why? Because the normal stress both are what? In what? Compression. Well, stress A, one is in compression, the other one is in tension, the magnitude will be lower. So now we have to now sketch out element C. Okay. So element C now will look like this. Or yeah, I'm going to draw from this view. Okay, this is I'm going to draw the hidden detail. Okay, this is your, and we know element C is going to see, let me change color. We know that it's going to see as X. Okay, so I'm trying to now sketch, okay, our transformation. So I know that this is our X, and I've flipped this up. This is my now my Z, and over here now is my Y. So this is my transformation relative to our element. Okay, and then if you look at how the torsion, right, is dealing that, so we're going to have a torque moving in this direction, right? The torque is moving in this direction, so the other side, the torque will be, let me change color, I do apologize. So we know that there's a torque, right? Right, we know that there's a torque going this direction, and the other one is going this direction. Okay, so by looking at the torque, right, so this torque over here is tau intersecting planes x, z. Okay, so this side is tau z x. Okay, so from here we have to find our normal stress x, and then our shearing stress. Okay, then we construct our 3D Mohr circle. But before we go on, we have to now construct we have to sketch our 3D Mohr circle to see how the circle look like. And the reason why we have to identify which condition is in. Is it in equation? Can we use equation number 3? Can we use equation number, or just focus on equation number 2? Now we don't know yet. So now we have to sketch the what? We have to sketch the Mohr circle to see whether our Mohr circle appear like this in 3D, or it appear like this in 3D. Okay, so now we sketch. Just simple sketch. Okay. So from here, I'm going to copy the whole thing, the transformation. Right. So I'm going to label this. This is our X. This surface over here, our Y, and this surface over here is our Z. Okay, so that's our, okay. So this is, again, as I repeat, this is just a what? This is just a sketch. So we have normal stress, right? And then we have our shearing stress. And I'm going to focus on the negative because we are working more on the negative, right? So this is our normal stress. This is our shearing stress. Element rotate clockwise. Element rotate anti-clockwise. Okay. So now we know that point Y has zero stress. This is our point Y. And point Z, okay, so point Z is going to have a element rotation in a anti-clockwise direction. So if we just look from here, okay, we realize that it's rotating anti-clockwise. So this is our let me sketch our shear first. Okay, so this is our shear value. Okay, so this is our, again, this is our shear value. So over here, this is my point Z. And then I will have my normal stress value. So this is my so this is my point Z. Sorry, point X, right? Over here, this is our point X. So we can draw a line linking them. Okay. And then again, we know where is our stress average. Which is over here. All right. So now we can sketch our 3D Mohr circle now. Okay. So this is one of our circle. Hey, sorry. Give me another 5 minutes, then we take a break. So this is one of our circle. Okay. So this is one of our circle. So this circle belongs to our XZ plane, okay, which is our in plane. And then another circle right, we have another circle which is over here. Right, and this corresponds to our YZ plane, which is our outer plane. And then the last circle okay, so this is our last circle. In our last circle, this belongs to our what? Our YZ plane. Okay, this belongs to our YZ plane. So this is our outer plane again. And over here, this is our stress A. And over here, this is our stress B. So from here, we realize that our Mohr circle that we've just drawn, right, is similar to this condition, right? Similar to this condition over here, right? So the tau max we have to use, right? For this case, the tau max is equal to half absolute value of stress max minus by what? Stress mean. Because your minimum, your maximum stress is not equal to what? 0. Okay, so you have to construct this 3D Mohr circle to see which condition we can use. Okay, I'm going to take a break now. We come back at 8:20. Lee, sorry, you have a question?
Yes.
Yep.
Can you go to page 4?
Yep.
Yes. My question is, why do you pick element C rather than the element
Because both of these
A.
values are negative. It will have the highest magnitude. This
Okay,
one is negative, one is positive. It will not be the highest. The other one, the bending moment are equal to what? 0. Okay.
Okay, I see. Yeah.